All right, so in our previous video, we got to see how we would do molecular geometries for things that have between 2 and 4 electron groups. But what we're going to be doing in this time, oh, my camera's like falling over here. What we're going to be doing in this video is taking a look at things that have geometries between 5 and 6 electron groups. And so we're going to take a look at PCl5 because it's really a classic example of this, and it's really simple to draw. We've drawn it already. So it's phosphorus, and it has 5 chlorines all attached to it. Each of those has their own lone pairs. And so this is our this is our Lewis diagram for PCl5. But now let's take a look at, I've been doing this in red. Let's keep the trends continuing here. So let's look at the electron group geometry, the molecular geometry, and the bond angle in this structure. So we should probably take a look back at our chart. And if we're taking a look back at our chart, we see that 5 electron groups is called Trigonal Bi-Pyramidal. And so what I want to show you is what this actually looks like. It looks like this. Now, it is called trigonal, which we learned last time, means like 3 parts. Bi-pyramidal, which means 2 pyramids. So to show you how this actually works, I'm going to pop 2 pieces off. And right in the center of this molecule, if I take like the top and the bottom off, this should hopefully be a familiar shape. A flat, 3-sided piece that looks like a triangle. This is trigonal planar, but let's add another piece on top. So now we kind of have like a little 3-sided pyramid. A trigonal pyramid, but there's also one on the bottom. So we have trigonal bi-pyramidal. It's kind of like stacking 2 pyramids together with the bases touching. And so you have like 2 points sticking up and down. And you end up getting this structure. Now, this structure, we're going to go back to our chart, has the same molecular geometry because there are no lone pairs. And so the molecular geometry is also, in this case, trigonal bi-pyramidal. But it does contain my favorite molecular geometry. And I know that probably seems weird that I have a favorite molecular geometry, but it's this one, the Sawhorse, which I learned to be called the seesaw. And so basically what happens is one of these atoms that's kind of in that trigonal planar part in the center gets popped off and gets replaced by a lone pair, and you literally get something that looks like a little seesaw. You can actually like rock it back and forth. Pretty crazy, hey? Now, this is one of the few things where it has multiple bond angles. And so what I wanted to show you is right here. From here to here and here to here. So remember I showed you there's that little like pyramid in the center. That little pyramid in the center still has the same bond angle. It's a 360-degree circle divided into 3 sections. So it has 120 degrees as one of the bond angles in this molecule. But as soon as we add a piece on the top, we now have made a 90-degree angle from that spot to that little trigonal planar piece. And then you also have one at the bottom that still has that 90-degree shape. So trigonal bi-pyramidal is the only shape that actually has 2 bond angles when it doesn't have any lone pairs surrounding the central atom. And so that is our trigonal bi-pyramidal. We're going to do one more example. In this other example, I'm going to use SF6. So when you draw this molecule, you get sulfur, fluorines, and you need 6 fluorines. So clearly you're violating the octet rule. And again, I'm going through this fast because this is a video about geometry. It's not a video about Lewis structures. So hopefully you feel comfortable drawing Lewis structures by now. But you end up with this structure. Now, if we were to count the number of electron groups, you have 1, 2, 3, 4, 5, 6. So your electron group geometry has to have 6 parts around it, and that is what we call an octahedral electron group geometry. Now, I would love to show you the 3-dimensional structure of this, but I don't have a model kit that actually has something that allows me to build 6 pieces around the center. So let's instead take a look at what our molecular geometry is. Well, there's no lone pairs in this molecule, so it would be octahedral. So we also have a molecular geometry that is octahedral. And hopefully one thing you've picked up is that when there are no lone pairs surrounding the central atom, the electron group geometry and the molecular geometry are the same. Now, in a molecule that is octahedral, there is only one bond angle. Everything in an octahedral structure is 90 degrees apart. And so that's what you end up getting is a 90-degree bond angle for everything in a structure that is octahedral. And so those are the electron group geometries that we see for things that violate the octet rule by having 5 and 6 electron groups surrounding them. So this is why it's going to be really important that you actually get those proper Lewis structures. Check your formal charges when you have things like phosphorus, sulfur, bromine, iodine, xenon in the center, so that you can see if they have geometries that are a little bit different. We care about geometry because structure determines function. The way that something is structured actually is going to determine the properties that molecule has. And so our first step towards determining the properties of molecules is going to be determining the shape of those molecules. So again, go practice, make sure you figure out you know what you're doing, and if you have any questions, again, make sure you ask, and thanks again for watching. See you next time.